Yeah, started. Go ahead.
So let me yeah. So our first problem is like maximum binary tree 2, and here we are given the node of a maximum tree, a tree where every node has a value greater than the other value in its subtree. Mm, I mean, he's comparing with the previous problem. The given tree was constructed from, I mean, a constructor was there for that, and recursively we are following the construct a routine. So these are the rules. If A is empty, you return null. Otherwise, if A of I is the largest element of A, you create a root node for that. And your left child of a root will be again this, and right child is I plus 1. Yeah, and we have to return the root. And we were not given it directly. You only need a, what is a constructor will be given. And suppose B is a copy of A, the value of val appended to. It is guaranteed that B will have the unique value. Yeah.
Okay, so they are referring to some previous problem, right? In this case.
Exactly. Yeah.
Okay, so that is, I think, the maximum binary tree one, correct?
One. Exactly.
Yeah. So in that they are saying that if we are given an array, okay, so if we find a midpoint or whatever, maybe a root whose value is largest, okay, so we take that value and whatever is remaining on the left side will be in the left side subtree, and whatever is remaining on after the max value node or maybe the cell, so that will be
Yeah.
the right subtree, correct?
Exactly. Yeah.
So if you see this example one, maybe the array actually was maybe it's like in order based. Okay, so it will be 1, 4, 2, 3, something like that. And so if you find 4, which is a mid, so we can happily say that whatever is to the left of that 4 will all be in left subtree, and whatever is to the right of that 4 will be in the right subtree, correct?
Yes.
So that was the whole problem.
There would be no warranty that the left subtree will be. I mean, the max on the left subtree will be larger or smaller than the right subtree, right? They don't mention that. And the example look like, it look like that, but the problem they don't mention, like when you pick the maximum one, then the left subtree could be another maximum. I mean, there's no guarantee that the left max of the left subtree will be smaller than max of the right subtree.
Yeah, that is fine. See, as long as your root is greater than both of the subtrees, okay, and the same thing you keep going down, okay,
Yeah,
so
yeah.
you're fine.
That's
It's
what
like
I'm
a high,
saying.
yeah, max heap, right? The binary heap.
Yeah.
Yeah. So yeah, that is fair point. So that's not an issue. But so the way they are doing, okay, in that problem, can we use the same thing over here? I'm just thinking loud, okay? So because that was more easier because that you could do recursively, right?
Yeah.
You just go through the array, you pick up whatever is the maximum. Yeah, you'll have to do an O of n traversal in that array. But whenever you get the max value, now you know the indices of your left and right subtree, correct? In that array. And then recursively keep on splitting that whole array.
But that's only the input. Now you have to add the value 5 to the tree. So you need to find, where 5 will be inserted.
Right, right. Yeah. So this is slightly different problem, right?
Yeah.
I was thinking like maybe, you take the whole tree, okay, you do an in-order traversal on the tree, okay, form an array, okay, and when you get an array, now you have this 5. You insert this 5 in such a way that you can split the whole array into two parts again, okay, and then you again do the same thing.
recursively. Yeah.
Yeah, recursively, because that looks much easier to implement. In the worst case, if we are not able to understand or get to how we can do this, because it's slightly trickier to do, right?
In
You
this case.
mean insert file into the yeah, but where can we insert file?
Yeah, in that case, if I do in order traversal of this current example one, so I have 1 4 2 3. Okay, so I will insert actually after 4 and 3.
Okay.
Yeah, so yeah, your question actually makes sense too, right? Yeah, so why only between 4 and 3 and not between 1 and 4? Correct, Leon?
Yeah, not between 4 and 3, but like, oh, let me see. But it return a tree, right? Not return an array.
Mm.
And
Yeah,
does
that
it
might be
return an
something.
array or a tree?
No, first we'll have to create an array and then insert that element, and again create a tree out of that, that
Oh,
array.
okay. I see. So you insert into an array.
Yeah,
I see. Yeah.
but then that will be again a problem where to insert on the right side or the left side. Yeah, that's a good point. Okay, so
Right.
that might not work, right?
Exactly. Yeah.
Why it might not work? I think it worked.
Because I'm
I
not sure where I'll put in.
example three. Example one, it worked, right?
No, if I put between 4 and 3, it's fine. So then the question will be why I'm not going to insert that array between 1 and that element of 5 between 1 and 4. Why I can't do that?
Well, if you put between 1 and 4, then what happened? But I mean, why it wrong?
I don't know, but if you do it that way, because if you look at the output of this particular example, it seems that the 5 is inserted between 4 and 3.
Yeah,
Because 5 looks to be 5's left subtree is 4, and whole of the left subtree is now the left of 5, right?
yeah, but 4 could be the right subtree of 5 too, right? Would that be okay? As long as let me see.
Yeah, I think what they have done in this case is they have inserted that 5. Okay, so if I have this as a in order 1 4 2 3, what they have done is they have inserted this 5 here. Okay, so when you insert this 5 here, now you know that this is your highest point. So you have this 5 as your root. Okay, and then this is your left subtree, correct, and your right subtree is empty in this case, right?
Is it post order?
It is pre-order, right?
Pre-order, then one will be your root, right?
Hmm?
But
No,
if you
no,
insert
I don't.
you insert 5, at the beginning of the array, that would be fine, right? Because it still satisfy the problem condition, right? As
Yeah,
long as 5 is a max.
that is correct. But the way the example they have shown here, this one, it seems like this. Correct. So I'm trying to follow what they have done there. So what you say also makes sense, because even if my 5, okay, like this, and whole of my this subtree of 4 is rooted to the right of this 5, I think that
Yeah.
should work, right? I don't know. I never tried it this way too, right? So if I have this should work actually as per them, because all of these are actually the root is always greater than each and every element, each and every subtree. Yeah, but no, I never tried that. So, but I think they have done it like they are appending it here and then they are doing it. But yeah, but I think that will be too much of work also. Maybe
Right.
sort of a brute force, right? Uh-huh.
Yeah.
So, what is the better way then?
Better than like the one you said, like you just compare the value with the root and check if it is lesser or greater. Depending on that, you put it on left or right.
Mm-hmm.
Kind of.
Yeah, so there would be 3 cases, right? If it greater than the root, then
Left.
it have to be the parent of the root,
Right.
right?
Yeah.
Mhm.
If it's less than the root, they have to go to the left subtree, and then otherwise I have to go to the right subtree. Oh,
Makes sense.
wait, no, if it's
It can go to
smaller,
anything. Yeah.
yeah, if it's smaller than the root, then it can go both left and right.
Yeah. So
Yeah.
we'll have to fix something, right? Okay. When we have a root, okay, whatever, if it is greater than that root, so as you say, that will become a root. In this case, 5 will become a root. And so whatever is the tree is, we'll just push to that left side of it. So we'll have to make some rules on our own. They have not mentioned anything like that. So I think either of it should work. Right. Even if you do
Yeah.
it the other way, that should also be fine, I think. That's interesting. But then if it is not, if it's not like the example one, if it is something to do with example two, okay, where we have to insert three, okay. So in this case, could you scroll down, Shashank, please?
Yeah, sure.
So here, actually, if you look at it, we are actually inserting the value 3, and this 3 actually goes to the right subtree, and it's put at the right of the on the right side of 4.
Okay.
Mm.
So in this case, your 3 is not greater than 5. So it looks to be like if the 3 is not greater than 5, then so you know that 3 will be somewhere on the left or right, but they prefer to choose to be on the right side. Okay, so you recursively go to the right. Okay, now you come at 4 and you still see that 4 is greater than 3. So because your 4 becomes the root now. Now 4 is greater than 3. So then again you go down to the right side and then you say it's null. And there you insert this guy. Okay. So your
Yeah.
fourth right will be pointing to this 3 because it's a leaf. This 4 is a leaf. Okay. And if you go down to the right again, then it will be null. So there you put this 3 and then attach it to the right of 4. Okay. So there is some biasness over here, right?
In this case, yeah.
Uh, but if so, either we use right or left. The only thing comes to like when you in the example one, where the element what you are inserting itself is the greatest one. So at
Correct.
that
Yeah.
time, yeah. So then that parent itself will actually form a parent, and then it will take the whole subtree and put it on the left side. Yeah. So if you are taking all these things on the right, so you have to put something on the left also. So they have just divided that way, right?
Do
Next.
they mention that we have to insert in a way that the height of the tree is minimum?
I don't think so. Maybe. Are there any constraints like that? No, I think so. Nothing like
They
that.
don't have.
Nothing like that. Yeah. But if we, I'm just trying to see if I can put everything in the reverse way and it still passes the test cases. No, it fails actually. Yeah, you cannot actually do left and right. So it should always be the way they are saying.
Yeah,
Okay.
and then we have to understand why.
Yeah, that's not actually even in the problem statement. But maybe these are some of the rules, right? Uh, so if you look at the rules, what they are showing here, okay, if A is empty, return null. Otherwise, let A be the largest element of A and create a root node. The left child of root will be whatever the construct from A0 to A minus 1, and the right will be I plus 1 to length minus 1, right? And then return root. They are not saying anything like that. So how do we go which place?
Yes, yeah.
So then, frankly, unless we don't show these examples to the interviewer, okay, we won't be able to formulate our implementation also, right? Mm. So this is a very, it's not a good one, right?
Yeah. The way they describe is, we can put, like for in example one, we can put file anywhere. Right.
Mm. Okay, so whatever it is now, if they are saying it that way, but it's better get it clarified with him. Yeah, that's the only thing we can do.
Yeah.
Yeah.
So the one will like share it. It is like, I mean, if there is no root, so there is no, I mean, you just the last node or whatever value you have, you just put it in the tree node and return, right? And if your value is greater than the root, then your value will become the left, right? I mean, you put your value in the tree node and root will become the left child of that tree. Kind of parent I'm making here.
Mm-hmm.
Yeah. And you return t, and otherwise root dot write again. You pass root dot write comma then val. Recursively it will again, what is it? Do same thing. So like only one condition I'm taking care of. If it is greater than, make root the left child of the current node.
Mm.
Yeah.
You always insert it to the right tree, subtree.
Yes.
So always insert to the right subtree, and when you are at the root, or maybe the element what you are inserting is greater than your root value, then it is to be the left side.
Yeah.
So your element will be at root or whatever that position, but he will move all that subarray to the left side.
Left side. Yeah.
So they are balancing it that way, right? So you push everything to the right. And so when you come to all the way to the right at the very bottom, and if your root is null, because you are at the leaf at the time, so you can just insert to the right
Value.
or maybe left also, whatever it is. Yeah.
Yeah.
Interesting.
So any other approach?
So if you in the, let me see, let me try to annotate it. So let's see, you are somewhere. Okay, so it happened that you need to insert the new node here. Then it's gonna go to line 12, right?
Yeah, value is greater than root dot val.
So it will go to the right, so it will come there. And so you are saying this guy actually, the value what you are going to insert. So this one actually, the whole of this subtree, what your arrow is, will move to the left side
Of that node. Yeah.
Yeah.
That means it what you say? Here your new root will come, and this will connect with this, and this will become your left. This will go to the left.
Your new root will be pointing to the left of this root, the original root of this tree, right?
Yeah,
And the
this.
whole of this will move to the left side. Okay.
Oh, is it moving, or you insert the new node to here, and then the existing one will become a child of the new node? Are you switching the left to right? I mean right to left?
I'm switch. Come again. I didn't get.
Why you insert the new node in here, right? That
Yeah,
will
yeah.
that new node become a left. Okay, and you put it in. Oh,
I'm creating a new node there, right? And to the left child, I'm putting this root over there.
Oh, okay.
Uday shared something.
Yeah, Uday, can you explain something of
Yeah, yeah.
whatever is there?
That is explaining why we have to insert into
Your voice is
so that article is explaining why we need to insert it into right separation.
Okay, he's saying that the article explains why it is that way, why it is to be the right side and why it is to be the left. Yeah.
Just considering that new element as a extension of the array.
Hmm.
So you have already constructed the sub tree, which means that the already array is already given, and this is a new element to the right side of that array.
Okay, so it is to the right side
So
of the
in
array.
that case, yeah, so in that case, you would have inserted at the right subtree. The, so they are taking that approach and explaining it in that.
Hmm. Okay. So anytime whenever we get an input, so we just have to insert. Now in the case where we were discussing uh, where it is going to be, so 1 4 3 2 1, so it will be at the right side and it is going to be the end of the array in this case. And for the example 2, when we have 1 2 5 4 and we want to insert 3, so that should be okay, 3 will be actually, yeah, again it will be the right side of the array, right, in this case also. Okay, so every time it is going to be right side of the array. No, not in this case when it is in the third example. So in the third example it is going to be which is 4, which will be between 5 and 3, but it will be after 5. Yeah, so then that is right. So you cannot insert between 2 and 5 in example 3, right? Hey Shashank, are you sharing the screen? Okay, you are not sharing, right? Okay.
no, I'm not sharing.
Okay, so what I was saying is,
Yeah.
so the way he is explaining in that article, so
Okay.
now this 3, okay, here, so it will be inserted this 3, example 3. So when we
So
form another array, so it will be inserted here between 5 and 4, but it cannot be inserted here as per that document explanation,
Hmm.
right? Yeah. You had something to say? Oh,
Yeah, somebody was saying.
yeah. Was it Abhishek or Praveen?
Sure.
Sorry.
Okay, let's
Praveen,
move.
you had something to say?
no, I'm still trying to understand, though it's clearly mentioned in the problem that the value will be appended. The last statement for this problem. Go down, down.
The last line, yeah.
Yeah. So suppose we copy and the value appended to it.
Okay, so you always append it to the right side of that array. Is it so?
I mean, either it should be at root or right side. Is not that the case?
Okay, so in this case, when we have an example 3, and if I form this array, right? So if this example 3, right? So what I will form if it's in order 1, so it will be 1, 2, 5, and 3, right? And so now I have to insert 4. In that case, if I insert it 4 here, uh, then will that be the way? So if I actually do it this way, so I come with 5, and then I'll have this right subtree, sorry, left subtree, which is the same. And then now this is my right subtree. Okay, in that case, how do I insert the first one? I go first insert 3 here. Okay, and then come with 4. Okay, so in that case, my 4 will be here. Yeah, okay, yeah. What you say makes sense.
Yeah.
Right, because your 4 is the biggest one. So that will be the root, and then 3 will actually be on the left subtree of this one because it doesn't have any right subtree. Okay, so you always have to insert at the end. That is the reason it says, or whatever Shashank also did the same thing, right? So
Yeah.
you first you keep on looking for the right, okay, till you don't come to the root or don't come to the leaf node, and then only you insert it. So you come to the leaf node, you insert that, and if it is greater than your root, then you make that as a left subtree.
Left side.
Okay.
When you say append at the end, right? So, yeah.
Yeah. So that is what it says. Like if you form an in-order traversal of this whole example, any example, and then you just append it to the end of it, and then you again reinsert the whole thing, so you are going to get exactly the way it is. Makes sense. Okay, cool.
Can you move back to example 1?
Sure.
So we append 5, right?
Yeah. So in this case, this is much easier, right? So if I even draw this one, so it is going to be 1, 4, 2, and 3, right? And then I append 5 to this one. So I know now this is my root, and this whole is going to be my left subtree, right?
Oh, you do the in order traversal?
Yeah.
Yeah.
Okay.
Okay. Thank you. Thank you, Uday. Thank you, Praveen. That was clear, right?
Yeah. Now it makes sense.
Okay. Let's. If there are no questions.
So can you go
Yeah.
back to Shank?
Yeah. Sure.
I'm still actually struggling to understand this problem. So let's go to the example 2.
Okay.
So if it's in example 2, instead of 4, it's 3.
No, he's trying to insert value 3.
So
3.
I'm
Yeah.
saying that 2, oh sorry, let me 2, 1, and 3. Let's say this is my original tree.
You should have 4 instead of 3 there.
And why?
If you are saying that's the original tree, so that is what it is.
Yeah, that is my okay. I mean, I want to simulate like that, but this is my original tree, and I want to insert the value 4 now.
Okay.
Oh. Yeah.
So how do you do? Okay. So in this case, if the way the logic, what I was thinking, if I form in order of this, it will be 2, 1, 5, 3. Then I will insert 4 at the end. Okay. So my 3 and 4 will still be on my right subtree. So 4 is greater, so it
So
will
you're
be
saying that
the root.
it should like this 1,
Oh.
and then 4. It will be
and then
like 3.
left will be the 3. Yeah. So in that case,
Okay.
it is going to be this way, right? Yeah.
If okay, so why actually it's not 5, 4, 2, 1, and 3? Why is not that?
Because as per the problem statement, right, you have to append your value which you are actually putting at the very end.
Last year. So after
Okay.
one also we could have done, right? If it
After
is the
one,
end, yeah, I mean original tree, one is there, right? Last node, at the last level.
Mhm.
So
you
there,
can,
so
because 4 is greater than 1, also
Yeah,
greater than 2.
actually, yeah. So actually, when you actually do the in order on your final tree, so the value should come up at the end, the appended value, right?
Mm-hmm. Yeah.
Okay.
so I mean it's fixed like in order only. But post order, if we do, in that case, it that
Well,
code won't.
Sorry,
okay.
pre-order. So you have to do the pre-order. Are they doing pre-order?
No, actually, I was doing the
They are doing in
order.
order actually, in order traversal. So the value should be at the end. So like if you see here, so 2, 1, 5, 4, 3,
Yeah.
right? So in order, so value should go at the end.
Right. Right.
Okay, so that's why it should be on the right side.
Mm-hmm. Yeah. Then it makes sense the way they are doing it, right? So it
Yeah,
will always be at the right position.
yeah. So
Mm.
that appended makes sense. So that the when you do the in order on your final tree, so the value should be at the last index.
Yeah. But they are saying that you should imagine it this way, but when we're implementing, it's not being implemented that way. But only thing when we have to implement, the way Shashank also did is like you go to the, if your value is lesser than your current value, or the root value, you keep on going to the right side
Yeah,
till you
only
don't
the
hit.
right side. You cannot go on the left side.
Yeah, yeah, yeah.
Okay.
Till you don't hit a leaf, and when you hit a leaf, then only actually you make that node, and then you adjust your left subtree accordingly.
Right.
Interesting. Yeah, because we have to always insert at the end, therefore we have to go to the right part always, right?
Yeah, it's a bit difficult to understand the problem.
Yeah, yeah, yeah. Yeah, it's very simple
Frustration.
though. Yeah.
Yeah.
Now it is clear. Okay. So the way you,
Yep.
yeah,
Yeah. Thank you.
yeah, thank you.
Yeah. Next is like our Minesweeper game. Yeah. So okay. So we are given a 2D matrix with characters in the board, and M will represent your unrevealed mind, E for unrevealed empty square, and P represents the revealed blank square that has no adjacent. Okay, the coordinates. And digits are there from 1 to 8 in the form like in the characters. Okay, and how many minds are adjacent to this revealed square? And finally, X represents a revealed mind. Now, given the next click position, I mean row and column they'll give among all the unrevealed squares, we have to return the board after revealing this position according to the following rules. So these are the rules. Okay. So if a mine M is revealed, then the game is over. We need to change it to X. And if what do you say? If empty square with no adjacent mines is revealed, then change it to the revealed bank B, and all of its adjacent like unrevealed square should be revealed recursively. Okay. And if there is an empty square E with at least one adjacent mine is revealed, we need to change it to a digit representing the number of adjacent mines and return the board when no more squares will be revealed. Yeah. Okay. The terminology to what do you say? M stands
Right,
for
right.
yeah.
So there are only two things initially, So if you look at it, so it will be M and E only. Okay.
Empty unrevealed ones. Yeah.
Yeah. So M stands for the mine, okay, and E stands for empty or the unrevealed. So unrevealed can have anything. I don't think so. Unrevealed can have anything, but only thing when we do all these, uh, click on it, that particular position, then you have to fill in those values.
In that case, yeah.
Yeah. And when he's saying you need to fill in the digits, so you need to find for each and every digit to all its four, up, left and right, all those four cells, and top and bottom. And if you find a mine at that in any of its neighbor, then you have to increment that value. Okay, or
Okay.
else you will just make put it B, right? So
Yeah.
that's the only thing. And so if you see M, you don't do anything at M. You first of all, if you first find M, then you return there itself. Okay, and
Okay.
then I think you have to put X in that case, right? Okay, for M.
Yeah.
Okay. Yeah, so there are many things what they have described, and slightly not very well explained, I think so. But yeah, it's very simple. You have E and M, and then you have to form it this way. The output what you are showing here, correct? Right. So you do it recursively. That is what it's trying to say, correct? Hmm.
Yeah.
Because initially when I looked at the output, I thought, okay, all these 111 represents mines, 111 mine, and then I couldn't really understand why it is saying 111 mine, and you still have an M in center. Okay, so
Yeah.
that was the confusion. Yeah, but he's saying it's not that. So on that particular cell, if you look to any of its side, it has to have a mine. Or is it the diagonals also? Because if you look at the 0th row and first column, you have a 1 there, but your mine is on the first row and second column, correct?
Second. Yeah.
So I think you have to look at the diagonals also, right?
Yeah.
Yeah, all the four
Correct.
diagonals.
Yeah.
It says that, yeah. So all the 8 sides you have to look, and if you find any mine, then you put that number in that particular cell.
It looks like backtracking, like not backtracking. I mean, what it's
You can say if you are using backtracking, you can say it can be DFS,
yeah,
right?
DFS. Yeah.
Yeah, that is a possibility. Or else you can use BFS also.
Yeah.
Yeah,
But
either of both should work.
DFS you can take wise decisions, right? Like if you don't fulfill this condition, then we won't be proceeding. Like these all the four. Yeah. I mean BFS should also work because they are not asking for any shortest or something like that. But it should work. It's a matrix. Yeah.
Yeah, it is not asking for shortest path for sure.
Yeah.
And there is no early termination, but we still have to explore all the paths because you have to recursively unravel the, you have to reveal the unrevealed ones, M and E's, right? So
Yeah.
you have to do that by going through all its adjacent, yeah. Yeah, so it doesn't matter BFS we use, but we are not taking the advantage of BFS, right? So it is almost going to behave like the way DFS is going to behave, right?
That's good.
Yeah, but there won't be any backtracking because once you have unraveled that particular cell, that's what it is.
We are done. Yeah. So normal then what is it? Yeah. I mean going through each cell of the matrix and satisfy the conditions.
Yes. Yeah. So I think that way the problem is not so difficult.
Conditions are like keeping these things in mind. I mean, if you get in interview, presence revealed, all these like pointers, what
Yeah,
are things?
I
Yeah,
agree. So it's not so. But first, understanding the problem and then formulating some sort of an approach itself will take some time. Looking at so much of things to take care of. Yeah,
yeah.
I understand. So I have a BFS approach only. I don't have a DFS, but if anyone has a DFS to share, that's fine. Okay, you shared something. Okay, was
No, I haven't done it.
okay. That is. Okay, I'll just share this way. Okay, so it's a very simple normal BFS. So this is our board, right? The input board, what we get, and then I'm creating another resultant output a 2D vector, and then assigning board to that. And this is my click. So I'm getting the coordinates of the click, and this is my row and column. And if I get my M on the click positions, right, I just change whatever I have at this board and then return immediately. Or else I then go, I have this direction array, all the 8 directions, and then I start with the BFS with a queue, having having a pair. So I push the R and C in this one. That is a click, right? So you have to recursively go. So if you start with the BFS, you take out whatever is there, and then whatever I'm getting here, I'm just looking for what the character is. If the character is E, okay, so I know that it is unraveled, not a mine position, right? Okay,
Yeah.
so when it is not an unraveled mine position, so I have to look for the neighbors of each and every and find out if there are mines. Okay, if there are mines, then I just uh, add something like this, So just imagine for now this get mines, and if I pass in this parameter, okay, I will get whatever mines are to around all its neighbors. So if I get a mine, okay, and then I'll just update that as the number, what number of mines, whatever it is. And in case if I don't get a mine, then what I have to do is I have to go in all the 4 directions, okay, and wherever there is E, if I find E in that case, I'll surely push it to the queue, okay, but that particular this NRC what I'm coming here, okay, so because I go to its all its neighbors, right, in this case. So this is what I'm visiting the neighbors and then putting in the queue. But after I'm done with that, so I mark that particular cell to B.
Yeah.
So that's the only thing we have to do. Absolutely nothing. And if you see what the mines is, get mines function is very simple. It's the same thing again. You go through all these 4 directions, okay, and get the coordinates for each and every neighbor. And then if they are valid, okay, and if I find an M for any of those locations, I just keep on incrementing my count and then return that value.
Okay. Yeah. That's yeah.
Yeah. It is very simple, nothing big. It's very straightforward also, right? Yeah. So I did a DFS, but I think people have done a DFS and that is also very easy.
True. Yeah.
Yeah.
So any other we have? Like,
Anyone wants to share any of these other approaches? Okay.
no. Let's proceed then.
Basically, what I understand is that once we click a cell, it has 3 possible outputs. Uh, Either it would be empty, or it will be a digit, or it will be a mine.
Yeah.
Yeah, yeah, so if you click a cell, that is correct. So but whenever you click a cell, in that case you will still have to, like in this example, right? So you are clicking this particular cell. So our Minesweeper, right?
Yes.
That's what it is. So when you click this particular cell here, so you have to still unravel all of these, whatever possible recursively, you know. So you have to do it in such a way that you reveal most of these squares as much as possible based on the rule what is given, right? So only thing is, if you look at this one, this is not revealed at all in our example, so you cannot reach that.
Yeah.
So that is the only thing. So you reveal as much as possible, but as you are revealing, you just look at whenever it is you don't find any mines, then you say blank. So these are all blanks, right? These are blank. But if you find a mine in its neighbors, then you just put that number over here. So you can say these are the mines. Okay. And if accidentally when you click on this mine itself, the game is over most of the time, right? So in that case, if you click on this one, so all of these squares, the way they are actually the empty ones, they will always be there, but only your mine will be marked as X in that case. So
So
it will be
actually, uh, this process will happen if you click on a blank square, right?
right. So this is on the blank square, what we are
And
doing
if you
here.
click on a digit, then only that digit will be revealed and nothing else.
Well, okay, so the digit is also the same. So digit initially is also blank space. Okay, so if you even if you click over here, so in that case,
Yeah.
what will happen? You will actually go here. You can go here, right? Recursively, you can go this direction. You can go this direction, this one, and then you can go the diagonals like this for
Oh,
that. So I think these guys again will go in the other diagonals also. Okay, so I this also will be almost the same. It will reveal. Okay, but I don't think so. It will reveal the mine in that case, right? Yeah, mine is not being revealed at all. No. Yeah, mine is also being revealed. No. Yeah. No, I don't think so. So it is mine is always as is because we are not changing mine here also. Okay.
Yeah.
Yeah. So you have to look for only E, not for M in that case. So whenever you click on exactly on M, at that time only you have to reveal that M. Okay, and then you put X in that particular location. So that's the only thing. So it will show this way in the game. So when they say recursive, it makes more sense to go the DFS way, right? So
Yeah.
when you are at one path, so you know what are the neighbors are, then you keep going to the end, correct? So when you are coming back again, you know what your neighbors are. So you keep going that way. But whenever you are going to that each and every neighbor, you just look at what the value is. The value should always be E, okay, and not M.
Yeah.
So so based on that, it will make more sense, right?
It will go. Yeah.
Right. So if you look at this one now, the example, so it just says E is an M. Other than that, nothing. But whenever you click on M exactly, your game immediately ends and you just mark X over there. I think we have an example 2 is like that, right? Yeah. So if you see example 2, okay, and if you are playing and your current board is like this because you are playing and you revealed some of the mines, right? And then you
That,
click on mine. And when you click on mine, all other board positions are exactly the same. Okay, only it is changing the X in that case.
yeah, the X. Yeah.
Yeah. Other than that, nothing. So if you look here also, your initial board was like that, as if it was clicked here, and then when it was revealed like this, so this guy comes and clicks on the mine, and then you see it is mind is revealed, and other than that, nothing, nothing changes on the board, and the game is over.
In that case, yeah.
Yeah. Do you have any questions, Himanshu?
I think it is fine.
Okay, no problem. Thanks. So let's move to the next one.
Yeah. So next is like Nim Game. So we are playing the game with following a Nim Game with your friend. Heap of stones are there on the table initially, and you and your friend will alternate take turns, and you go first. On each of the turn, the person whose turn, you will remove 1 to 3 stones from the heap, and the one who removes the last one is the winner. Okay. So the number of stones, and is the number of stones. So if you can win the game, assuming both you and your friend play optimally, return true, otherwise return false. Okay. So 4 stones are there. First stones I removed it. I mean, one person removed it. So now we are left with 3, right? So
Okay.
second guy removed the second stone.
Mm-hmm. So if there are 4 stones,
Okay.
So you have chances of removing 1, 2, or 3.
Yeah.
So the max stones what you can remove, because you have to play optimally as well as your friend has to play optimally. Okay, so what you will do, you will remove 1 or 2 or 3, either of it you remove. Your friend also does exactly the complement of it, right? Yeah. So then he will win in that case. So having n as 4 is that you will be losing.
Yeah.
Okay.
So basically, the goal is we need to make sure that the other friend, uh, we shouldn't give the other friend 4, right? That's so.
You should not give other friend 4, or you should not get 4.
Oh yeah, yeah.
It-
I should not get 4 exactly.
right,
Yeah.
right, right. Mhm.
Yeah.
It looks like a DP one, right?
Yeah, I saw a lot of approaches using DP in that. Yeah, I didn't go that route. Yeah.
Because there are paths.
Uh,
Either you pick, I mean, first time you can pick 1 stone, or you can pick 2 stone, or 3 or 4, right? Now,
mhm.
depending on that, the other friend will again have different possibilities.
Okay, so
This is
then it's like a DFS, right?
yeah, DFS, you can say,
Mhm.
yeah,
Yeah.
bracket kind of thing. Because first friend has 4 possibilities. The second, depending on first, then 3 stones we are left. So 3 possibilities with second friend is there. For all this also 3. For the next level, it will go to 2 possibility
Mhm.
kind of.
So it's like whenever we get a value n, so the path what we would do is we take subtract 1 from each, so 1 from that n, then 2 from the 10, and then 3 from the 10. Okay, and then again do a DFS
On
from
that,
all those recursions, right?
yeah,
Recursive tree.
exactly.
And when we come at the end, so our base case will be like if we are lesser than 3, 1, 2, 3, only 1, 2, 3, not even 0. And if you are playing, so it means that you will win. But if you get 4, then you lose. And even if you get 0, then you lose.
Using again, yeah.
Right? Yeah. So that should work, right? But yeah, but it might be a problem.
Because we have similar problems which using DP, like same thing. Stone, you have stone game problem. There are 7 such problems. Stone game 1, stone game 2, 3, 4, 5, 6, 7.
Mhm.
Yeah, so there they follow DP and greedy approach. Mostly, I think DP. Yeah.
Yeah, but is really DP required?
Here, I don't know. Optimally, they are telling. But how will you decide? Like, how will you say that how optimally the previous player has played, right?
Hmm.
Like,
Yeah,
you
then.
don't, right? So, like all the possibilities will have to explore, and depending on that.
Mm. Yeah, so you'll have to exhaustively explore all the possibilities, and
Search,
therefore,
exactly.
yeah.
Looks like that. Yeah.
Mm.
The last is like if you just take the remainder of it, and if you are not left with anything, that means you won the. But that's not a good. I mean, what do you say?
What
Good.
do you mean by remainder?
I remember like what they are saying. If you are the last one to remove the stone, right? If you can win the, how do you win the game? The one who removes the last stone, right?
Mm-hmm.
So whatever, let's say 4, whatever n is there, right?
Mm-hmm.
Uh, if you take the remainder and the last stone, if we get some remainder and that is the last stone which I pick, then I'll win the game in that case.
Okay, so you are saying that if the n's value is 1, 2, 3, then
Yeah,
you win. So therefore,
yeah.
you are taking remainder of what? But
A remainder of uh, 4
okay,
because I think.
yeah. So if you take remainder of 4,
Mhm.
and if the value is 1, 2, 3, then you win. And if the value is not 1, 2, 3, then your friend wins.
Yeah, because for 4 we can have a remainder 1, 2, 3 only at max, right? I mean n minus 1.
Yeah, that is good. But like if your n is 8, 16, 24, So will that still hold true?
So
Yeah, it should, but the thing is, okay, if you start at 24th, okay, level, or you have 24 stone, so you start with one, and then your friend starts with one, and it's not very perfect in the sense like a human mind will work exactly to find the optimal path, right? Unless you're playing with a computer.
exactly.
Yeah. So because your friend also has to play exactly optimally, so for, at least you'll have to have this game with a human being and a computer, right?
In that
Or
case,
if like if you both are playing, then we will always play some weird way, right?
exactly, yeah, it won't follow. Yeah, because instructions will be fed like this in the system, but
Yeah.
human, I don't think so they'll follow.
But I think what he's trying to say is whatever the way it is, if it's 24, 16, 8, whatever the way you play, okay, still it will be destined to win that way. If it is division, the number is divisible by 4, okay, so whatever the way you play, because that is what he's trying to say. If you take 1, 2, 3, so it will always be your friend will win.
In that case,
Yeah. So even if you try the whole tree, okay, the recursive tree, you will still see that you won't return true. Okay, if you keep on subtracting 1, 2, 3 each and every time, and from all the 3 trees for, at each and every level for each and every uh, state, okay, so you will never come across a position where it will return true. It will always return false.
yeah.
So that is what it is trying to say, and therefore it says anytime if a number is divisible by 4, you won't win.
In that case,
So we can take example of like 8 and 16, because I was also imagining the same thing, what if I do it a very weird way, but it still says that you won't return true at all. You will always return false.
in that case, yeah.
So if it is not in that range, then it will return true. Very interesting, actually. So yeah, we'll have to actually make a case like that to explain if we are trying to solve the mathematical way, and just explain him the recursion function. Okay, and show why it's not going to be true. So we take an example of like 16 or 8, and then keep on saying, okay, we can expand on this, and then surely you're not going to return anytime a true value, because you're not going to reach 1, 2, 3 at all, right? So you'll have to have two players always, like yourself and the other player, and then maybe two different sets. You can always put one in the front side and one at your side. In the recursion, you can have a parameter like that, and then if you go that path, then you will come to a conclusion.
Yeah.
The way they say, yeah. In fact, it's a very nice problem, because it's solved. Everyone solves it using the mathematical way, and the reason why they do is because the Leetcode doesn't allow for the other approaches,
Oh,
right? Because it
yeah.
always TLEs. Even if you implement the DP way, it will TLE.
Is it? Oh,
Yeah, it TLEs every time, and that is the reason only this one passes. Because if you look at this, the time complexity is very high, very efficient. Okay, and if even if you use a single DP, or maybe even you do a DFS, which is very simple one, okay, but still doesn't pass because this has a taken the bar too high, right?
in
It is
that, yeah.
almost over 1 constant, right?
Yeah.
So it doesn't allow to pass all the regular ones. But I would say, yeah, we should do the other way also, and that makes more sense for an interview
More
question,
generic, that is, yeah.
right?
Actually, it is more like puzzle. I'll say advanced puzzle.
Yeah. But see, if this question comes in your interview, okay, even if you explain him, he won't be satisfied, as well as you also won't be satisfied, right?
Yeah.
No, I think the intent here was that you have to explain it in the same way with the rules. Like if you have 8 stones or 12 stones, and you have like 1, 2, 3, then probably the interviewer's intent is to come up with that approach only instead of the coding based approach. I'm thinking, say if you have 10 stones and you have rules from 1 to 4, right? Then again, the person who has 10 stones, if there are 10 stones, then the first person will always lose, right?
Yeah.
I mean, the intent behind is more like a generalized problem. Instead of say, here we see, right, we can pick from 1 to 3 and 4 stones or a multiple of 4. If we have 5, then anywhere from 1 to 4.
Yeah.
So we'll have to go step by step, explain it to him, and then and in case if he says, okay, now let's code, then we can use either the DP or the DFS way, or just tell him, okay, we can do it the mathematical way. So if he's satisfied, that's fine, or else then do the DFS way.
In that case.
Yeah, that makes sense.
Yeah.